Welcome to lecture number 9 for ECE 341, Random Processes. In this lecture, we're going to look at a discrete uniform distribution. When you think about a uniform distribution that's discrete, think about a six-sided die. When I roll it, I get the numbers 1 through 6. Each number has the same probability. That's a discrete uniform distribution. Now, a couple definitions. A uniform distribution is a distribution where the probability of each outcome is the same. A geometric distribution is the number of Bernoulli trials until you get a success. A Pascal distribution is the number of Bernoulli trials until you get R successes. These are lectures coming up, geometric and Pascal. This lecture looks at uniform distribution. Now for uniform distribution, the PDF is if I have uniform numbers between A and B, its probability of each number is 1 over 1 plus B minus A, basically 1 over n, where n is the number of numbers, like 1/6 for a six-sided die, times the delta function between those numbers. I can get the answers 1 through 6 for a six-sided die. The moment generating function is the z-transform. I've got, for a six-sided die, 1 in 6 chance of getting a 1, 2, 3, 4, 5, and 6. The mean is the sum of the two endpoints divided by 2. Like for a six-sided die, 1 plus 6 over 2, average is 3.5. And the variance is b plus 1 minus a squared minus 1 over 12. Or a six-sided die, 6 plus 1 minus 1, 6 squared minus 1, 35 over 12. Geometric and Pascal we'll get to later. Now, a uniform distribution is sort of like a Bernoulli trial, but for Bernoulli trial there's only two possible outcomes, 1 and 0. For a uniform distribution, there are n possible outcomes. Each one has the same probability. Again, example like a six-sided die, I can get the numbers 1 through 6. Each one has a probability of 1 in 6. So there's a couple examples where you get uniform distributions. For example, if I take a deck of playing cards and I draw a card, the probability of any given card from a shuffle deck is 1 in 52. If I'm playing roulette and I bet on a number like 10 black, the probability 10 black comes up is 1 in 31 in Vegas. In Atlantic City, 1 in 32. But that's because in Vegas they've got the numbers 1 through 30 plus the number 0. 0 is green, so if you bet red or black, you always lose. Bet a 1 through 31, green comes up, you always lose. That helps the house have slightly better odds of winning. In Atlantic City, they actually have two zeros. They've got 0 and double 0. Increases the odds for the house winning in Atlantic City. Vegas has got better odds than Atlantic City. If you play the lottery, ideally the odds of winning the lottery are the same, 1 in 78 million. Not entirely true. They've had cases in the history where the head of the lottery commission at a different country won the lottery 3 times, making you think that it's not random. But ideally, the lottery should be random. Odds of winning are 1 in 78 million. Any number you pick has got the same odds, 1 in 78 million. Being selected for a jury pool. Ideally, the odds are 1 in 15,000. So that's where 10 people are selected from a county of 150,000. If each person has the equal probability of being selected, you've got a 1 in 15,000 chance of being selected for a jury pool. Now, those are kind of ideal situations. In practice, sometimes things that are supposed to be uniform are not. For example, about 15 years ago, there was a case in Las Vegas. Somebody was winning in roulette. So roulette, they've got this wheel with 31 numbers on it. They spin a marble, marble lands on a spot. All numbers should be equally likely. Well, one person came up with the idea that wheels are built by people. People aren't perfect, therefore maybe these wheels aren't perfect. Maybe some numbers are coming up more often than they should. So he did kind of a study, looked at the different wheels, and found out that, yeah, some of the wheels were not actually equal probability. Some numbers were coming up too frequently. Start betting on those numbers and was winning. Well, if you start winning in Vegas, you get people's attention and try to find out why you're winning. Once they figured out what was going on, they kind of fixed that. Now what roulette wheels do is each day the roulette wheels are taken into a back room and shuffled around and brought back out. So you don't know which wheel was at which table each day. They also don't like it if you take notes. If you're keeping track of which numbers are coming up on a wheel, they ask you to please stop doing that. They will not let you touch the wheel. If you touch the wheel, they're afraid that you're marking the wheel, so you can identify it. If somebody touches the wheel, they get very upset. They might even discard the wheel, throw it out, bring in a new wheel, just to make sure that you're not going to win more often than you should. So, again, these are kind of ideal situations. Hasn't always been that case in the past. One other example, loaded dice. Example where numbers come up more often than they should. This is a problem they have in craps. In craps, what you can do is they used to be solid dice. So they would build dice and have a piece of lead on one side. So that one side comes down more often than they should. That affects the numbers that come up. So it's no longer a fair die. It's no longer a uniform distribution. To fix that, they start making clear dice. So you can't stick a piece of lead in there. But what you can still do is you can drill out the sixes and fill in the sixes with tungsten, some heavy metal, cover it up and paint it, make it look like a normal die. Now the sixes, more often than not, come down on the bottom, affects the dice. What they do in roulettes and dice games is that when it's your turn to throw the dice, you cannot cup the dice. They get very upset if they lose sight of the dice because you might be swapping them out with loaded dice. When you throw the dice, I got to keep the dice on the table. If the die winds up on the floor, they lose sight of the die. They won't let you throw it again. They retire that die, bring out a new set. Again, all sorts of schemes trying to avoid loaded dice getting onto the table. And even then, at the end of the day, there's always a couple loaded dice on the retired bin. But those are cases where things should be a uniform distribution, but they're not. But anyway, back at the ranch. Going back to uniform distribution, the PDF of uniform distribution is 1 over n, say for a 6-sided die is 1/6, times the delta function at each number, at 1, 2, 3, 4, 5, and 6. The z-transform is kind of like the definition. I've got a 1 in 6 chance of getting a 1, that's 1 over z, of a 2, 1 over z squared, 3, 4, 5, 6. The mean is the average, that's like for a 6-sided die, 1 plus 6 over 2, 3.5. The variance is b minus a plus 1 squared minus 1 over 12, 35 over 12 for a 6-sided die. And a thing to note, when you add distributions, the means add and the variance adds. That's why in statistics we typically use the variance. A lot of people like the standard deviation. We use that later on. But the standard deviation doesn't add, it's the variance that adds. So to illustrate that, let's do a bunch of different examples of dice. So dice are a good example of uniform distributions. When I start combining dice, I'm combining uniform distributions. So let's look at a couple Dungeons & Dragons spells. If you're into playing Dungeons & Dragons, you might know these spells. Otherwise, just think of it as adding a bunch of dice. Level 0 spell, Frostbite, does 1 to 6 cold damage. You roll a 6-sided die, and that's how much damage you do. Thunderous Smite is a paladin spell. I roll 2 6-sided dice, and my weapon does that much extra damage next time I swing. A Mind Whip does 3 6-sided dice of damage. I roll 3 6-sided dice, add them up, that's how much damage I do. Thunderstep is 3d10. Ice Storm does 2 8-sided dice plus 4 6-sided dice. In D&D, this is how they write it. 2d8 means 2 8-sided dice. 4d6 means 4 6-sided dice. Chain Lightning is 10 8-sided dice. Meteor Swarm, highest level spell you can cast. 20 6-sided dice plus 20 6-sided dice. 20d6 of bludgeoning damage, 20d6 of fire damage. You get hit with Meteor Swarm spell, you're hurting. Let's find out the PDF for each of these. Now the first level, or 0th level spell, Frostbite, is pretty easy. That's just a 6-sided die. The PDF is just 1 in 6 chance of rolling the numbers 1 through 6. That's pretty much it. The mean and variance for a 6-sided die. The mean from the formula is 3.5. The variance is how far each number from the mean times its probability. That winds up being 2.91167, or I can use the formula 6 minus 1 plus 1 squared over 1, 35 over 12 is 2.91167. Either way works. Harder problem. How much damage does a thunderous smite spell do? What's the PDF? And I also want to find the mean and the variance. Now what Thunderous Smite does, that's a paladin spell, level 1 spell. Your weapon does an extra 2d6 of thunder damage. To calculate the PDF, there's a couple ways of doing that. I can do Monte Carlo, I can do enumeration, I can do a moment generating function, I can do convolution. Now with Monte Carlo, again, we've used Monte Carlo a couple times in the past. What I could do is roll 2 6-sided dice. That's what this does. Take 2 random numbers times 6, round it up. That's 2d6. Add them up. That's how much damage I did. Repeat a million times, keeping track of how many times I did 1 damage, 2 damage, 3 damage, 4 damage, and so on. When I'm done, this is what I get. This is the probability of each number times 36, just because there are 36 different combinations. So this is basically the number of ways I can get 0. We get it 1 point out of 2 rolls, 2 points, 3 points, 4 points, 5 points. All that divided by 36 gives you the probability. Second approach, enumeration. I can go through every combination of a 6-sided die, count what the sum is, and count how many times it did 0 damage, 1 damage, 2 damage, and here's what I get. There's no way to get 1 damage, one way to get 2 damage, 2, 3, 4, 5, 6. That's using enumeration. And kind of note with enumeration, the numbers are exact. Monte Carlo is close, a little bit wrong because it's random, but close. And the numbers match up. Monte Carlo matches enumeration. The actual odds would be the count divided by the total number of rolls divided by 36. That's why we multiplied by 36 last problem. So these two numbers kind of match up. That's the second option, enumeration. A third option is moment generating functions. This is the z-transform for a 6-sided die. 1 in 6 chance of rolling a 1, 1 in 6 chance of rolling a 2, 3, 4, 5, and 6. For 2d6, I multiply the z-transforms, or this guy squared. Put that over a common denominator, it winds up being this polynomial squared. Now when you multiply polynomials, you're using convolution. So you're kind of stuck with convolution. Fourth approach is convolution. What I can do in MATLAB is have the PDF for a single 6-sided die. So this is the probability of rolling a 0, 1, 2, 3, 4, 5, and 6. I could keep on going, but it's not necessary. So that's the PDF for a single 6-sided die. If I can involve a 6-sided die with a 6-sided die and plot it, here's what I get. Same answer I got before, so there's a 1 in 36 chance of getting a 2, 2 in 36 chance, 3, 4, 5, and 6, 5, 4, 3, 2, 1. Where that comes from is when you multiply polynomials, you're really doing convolution. When I do convolution, I can involve a 6-sided die with a 6-sided die, flip it, sweep, get the answer, or MATLAB does it for you. That's the PDF for 2 6-sided dice. Now to calculate the mean and variance of 2d6, there's a couple ways you can do that. One is I can apply the definition. The mean is the average. So here's the numbers 1 through 12 times the probability of numbers 1 through 12. Add it all up, I get 7. The variance is how far is each number from the mean squared times the probability of each number. Add it all up, I get 5.8333. That's the variance. That's one way to do it. A second way is to scale it. When I add 2 6-sided dice, the mean and variance will be double the mean and variance of a single 6-sided dice. So here's the mean of a single 6-sided die. When I double it, I get 7. Same answer. Here's the variance of a single 6-sided die. When I double it, I get 5.833. Same answer. So either way works. That's 2 6-sided dice. Let's try another spell. Thunderstep. Thunderstep is a sorcerer spell, level 3. It has 3 10-sided dice of thunder damage. Now to find the PDF, there's a couple ways of doing it. I'm just going to use convolution because it's easy with MATLAB. So here's the PDF for a single 6-sided die. Here's the probability of rolling a 0, 1, up to 10. Those numbers divided by 10. Each one's got equal probability. It's a uniform distribution. Probability is 1/10. That's a single 6-sided die. It can involve 2 of them. That's 2d6. It can involve 1d6 with 2d6. I get 3d6. So that's the PDF for 3 6-sided dice. If I do a bar chart, here's what that looks like. And again, I've got this bell-shaped curve. That's with only adding 3 dice. That's the central limit theorem. One more time. I keep on getting that bell-shaped curve. That's a normal distribution. That's something we'll be talking about later. A really important distribution. The mean and variance for 3 10-sided dice can come from a different approach. A couple approaches. I can use the definition. What is the weighted average of each number? I get 16.5. What is the weighted distance to the mean squared? That's the variance, 24.75. Or I can just take a single 10-sided die. Here's the mean and variance. Scale it. So 3 10-sided dice should have a mean of 16.5. That matches up. The variance should be 3 times 8.25, 24.75. That matches up. And these are numbers we're going to be using later on. Ice Storm. An Ice Storm is a sorcerer, wizard, or druid spell. It's a 4th level spell. Does 2 8-sided dice and bludgeoning damage, 4 6-sided dice of cold damage. So what's the PDF for the damage done by an Ice Storm spell? Well, again, a couple of ways to figure that out. I can use convolution, other methods. I'm going to use convolution because, again, with MATLAB, it's pretty darn easy. Here's a 6-sided die, 2 6-sided dice, 4 6-sided dice. And kind of note, I don't have to keep on going by ones. If I do a 2 and a 2, I get 4. 4 and a 4, I get 8. 8 and 8 get 16. I can do it that way. But anyway, I've got 4 6-sided dice. Here's the PDF for an 8-sided die. Convolve it, I get 2 8-sided dice. Convolve 4d6 plus 2d8, I get Ice Storm. If I plot the damage, there's the damage for an Ice Storm spell. Again, this bell-shaped curve, one more time. Ice Storm has a mean and a variance. The mean, if I calculate it, is 23. The variance is 22.1667. One way to calculate it. Another way is just take a 6-sided die, find its mean and variance, 8-sided die, its mean and variance, and then do a weighted average. For 6-sided dice, would be take the 6-sided die times 4, 8-sided die times 2, add them all up, I get 23. For the variance, I have 4 times the variance of a 6-sided die, plus 2 times the variance of an 8-sided die, add them all up. That's the variance for the total. Same answer. So how you do it doesn't matter. You're going to get the same result. So that's kind of a uniform distribution. It's one way to think about it. It's all about dice. Different types of spells roll different types of damage with dice. Using uniform distribution, I can find the mean, find the variance, find the PDF. All fairly easy with MATLAB. Switching gears a little bit. Here's an application of the uniform distribution. Now, suppose I have a population of size n, and each item is labeled 1 through n. I then sample k items at random from that population. From that sample, how do I calculate how large n is? And again, I'm going to assume that when I collect those samples, that's a uniform distribution. Every item that I sample has equal likelihood of being sampled. Well, a history of why this problem is important goes back to World War II. It's why it's called the German tank problem. Back in World War II, the Allies, specifically England and United States, had a problem. The American tanks could not stand up against the German Tiger and Panther tanks. That's kind of why the Germans called the Sherman a Tommy cooker. When you hit a Sherman tank, it caught fire, cooking the people on the inside. Well, our tanks couldn't stand up against a Panther or Tiger, and that was going to cause a problem. D-Day was coming up. If the Germans had thousands and thousands of these tanks, we would be in deep trouble during D-Day. What that meant is we would have to postpone D-Day and start bringing over more heavy tanks, like the Pershing heavy tank. And we couldn't have D-Day until we had enough Pershing tanks to give us a fighting chance against the German Tigers and Panther tanks. On the other hand, if the Germans just had a handful, say maybe a couple hundred, Panther and Tiger tanks, they would not affect the outcome of the war. They'd be a problem, but there's just not enough of them to change the outcome. So how do you tell how many German tanks or how many Panther and Tiger tanks the Germans had? Well, we had information. We had intelligence telling us that there were thousands of tanks being built every month. We also had information from actual tanks. When we would capture a Tiger or a Panther tank, it had the number of the tank printed right on the side. That was the production number. This is the 141st Tiger tank that was built. In addition, the gearboxes were numbered. In addition, the tires were numbered. So we had a sample of the tanks with the production number. From that, can I estimate how many tanks exist? That's called the German tank problem. Well, there's a couple ways to approach that. From a statistical standpoint, what they wound up doing is look at the number of tanks that you sample, K, the largest number that you have in that sample, M, and from that estimate N. And kind of three different approaches that were used. There's the frequentist approach. You have the capital N, the number of tanks is roughly M. So if I have like 141 for one of the tank numbers, I know there's at least 141 tanks being built. Plus M over K minus 1. That's one approach. A Bayesian approach says N is roughly M plus M log 2 over K minus 1. A third approach is the Bayesian confidence interval. I'm going to say that there's somewhere between mu plus or minus sigma tanks built, where mu is m minus 1 times k minus 1 over k minus 2, and sigma squared is this formula. So for example, using those formulas, here's what actually wound up happening. Is intelligence was saying that the Germans were building over 1,000 tanks every month, and likewise there'd be thousands and thousands of tanks the Allies would have to deal with. Based on statistics, it looked like the Germans were only building about 169 tanks, 244, 327 tanks during these months. Once the war was over, we went through the German archives and looked at how many tanks the Germans were actually building. And here's the actual number based upon German records. These statistics actually gave better information than Allied intelligence. Based upon these statistics, there just weren't that many German tanks out there, so D-Day could proceed, and it did. The result is we did run into a couple Tigers and Panther tanks. Some examples, like 10 hunting Tigers or hunting Panthers, ran into 18 Churchill tanks and just took out 11 of them within 10 minutes. They were a nuisance, they were a problem, but there just weren't enough of them to change the outcome of the war. So this is where statistics actually allowed D-Day to happen, even though intelligence was saying this is a bad idea, you're going to face major problems. Now, as an example, I can take those results and apply them in MATLAB. So let's generate, for example, n is a random number between 50 and 250. I'm going to take n random numbers and sort them. So B is the sorted order, that's like my shuffle deck from before. I'm going to sample 10 tanks at random from that deck. What are the top 10? So when I did that, here's the tanks. There's tank number 122, 98, 173, and so on. From the sample, how many tanks do the Germans have? Or in this case, what is N? Well, to do that, I need to know what's the biggest number from the sample. That's 174, is this number. And how large is the sample? That's 10. Now, using those different approaches, I can say the frequentist approach, I think N is M plus M over K minus 1. I think there's 190 tanks. Using the Bayesian approach, this formula, I think there's 187. With the Bayesian confidence interval, here's the mean, here's the variance. I think the square root, there's the standard deviation. It should be the mean plus or minus the standard deviation. So I think there's somewhere between 218 and 170 tanks. If I compare to the actual number, since I did this in MATLAB, I know what N is. If I look at it, N's actually 213. The frequentist, Bayesian confidence interval are all pretty close. The confidence interval actually brackets it pretty well. I'll get different answers every time I run this, but that's kind of an example of the German tank problem. If I have a uniform distribution of samples from an ordered set, can I estimate the maximum size of that set? That's a German tank problem. This has actually been used since then. Countries tend to classify how many items they have. If you number them sequentially, you can actually estimate how large the population is. So there are ways to counter that, such as they use random numbers rather than sequential numbers. I intentionally inflate the numbers to make it look like there's more than there are. Various ways around it. But still, people oftentimes number the things coming off the assembly line. From that, I can tell you how many items there are. So that's a uniform distribution. A uniform distribution is a distribution that has equal probability for all possible outcomes. A typical example would be the result of rolling an n-sided die. When you add dice together, you can find the PDF using several methods. I can use Monte Carlo, enumeration, or convolution. With MATLAB, convolution is probably the easiest. When adding dice together, the means add and the variance adds. And kind of note, this is kind of the oddity. It's not the standard deviation, it's the variance that adds. And finally, if somebody has a population where each item is numbered 1 through n, I can estimate the size of the population from a sample from that population. That's the German tank problem. With that, that's lecture number 9 for ECE 341, Uniform Distribution.